So far, we have looked at quadratic relations in vertex form, which looks like this. And when we look at vertex form, it tells us a number of things about that, the graph of that relation. A tells us about the direction it points, up or down, and then H and K form our vertex. So the vertex is coordinate H, K. So looking at a quadratic relation in vertex form can tell us a lot about that relation. But there is another form of a quadratic relation. It's the same relation, it's just another way of forming it. And that's standard form. The standard form looks like this. And what standard form tells us is, well, actually not as much as vertex form. In fact, all that it really tells us up front is that C is the y-intercept. But that can be useful. So if you're given a quadratic relation in vertex form, you can find all of this information. And then if you're able to convert it somehow, that's why we have this arrow here. If you're able to convert it to standard form, you'll also find the y-intercept. So let's take a look at an example. Perhaps we're given y equals 2x minus 3 squared plus 1. So we know a couple things about that graph. We know that because a equals 2, that it's stretched vertically, so it's kind of a narrow looking thing like this. We also know that its vertex is going to be 3, 1. But how do we get to standard form? It's actually quite simple if you know any algebra. You just have to expand the vertex form. So if you remember order of operations, bedmass, brackets, there's nothing we can really do in these brackets here. So exponents. And here's something that trips a lot of people up. X minus 3 squared is not, and some people will do this, they'll go, oh, x minus 3 squared is the same as x squared minus 3 squared. No, actually it's not. That, I can see how you'd make that mistake, but be careful not to. X minus 3 squared is actually the same as x minus 3 times x minus 3. Because remember, squared just means something multiplied by itself. And so if what's being squared is everything in this bracket, then it's x minus 3 times itself. So just be careful about that. So when you go to expand this, make sure you write that out in full. So x minus 3 squared is really x minus 3 times x minus 3 plus 1. Then whichever method you use, I'm going to use FOIL. Remember, FOIL is first, outside, inside, last. I'm going to go 2 times all of this. X times x is x squared. X times negative 3 is negative 3x. Negative 3 times x is another negative 3x. And negative 3 times negative 3 is positive 9 plus 1. Now we just gather all our terms together inside the brackets. And now it's a matter of expanding that expression. So 2 times x squared is 2x squared. 2 times negative 6x is negative 12x. 2 times 9 is positive 18 plus 1. And if we just gather that 18 and that 1 together, we'll be done. We will have it in standard form. So our final answer is y equals 2x squared minus 12x plus 19. So that's standard form, and what that 19 tells us is that the y-intercept equals 19. Let's do one more example. Another way we could look at problems like this is I could tell you something like, okay, I'm going to talk about a quadratic relation, but all I'm going to tell you is that in vertex form, a equals 2, and I'll also tell you that the vertex is 3, negative 1. Now put it in standard form. Well, we can't put it in standard form right away. First thing we have to do is write it out in vertex form. So we're going to go y equals 2 x minus 3, that's the h, squared, subtract 1, that's the k. Then we convert that to standard form by expanding. So we'll do this quite quick. X minus 3 squared is just x minus 3 times x minus 3. And the more you expand binomials like this, the quicker you're going to get at it. So it's going to be 2 times x squared, subtract 3x, and another subtract 3x will be negative 6x. Negative 3 times itself is positive 9. And finally, let's expand. 2 times x squared, 2x squared, and we get something like this. And then we just collect that 18 and that 1 together, and we have 2x squared minus 12x plus 17. So just using this information, we have come up with a standard form of that quadratic relation.